Welcome back to the Deep Dive. Today we're continuing our journey through the OEIS, the Online Encyclopedia of Integer Sequences. A great resource, especially for you number theory students.
Absolutely.
And our focus, it's a really fundamental one, A000041, the partition number sequence.
Yes. The first terms, maybe you've seen them, 1, 1, 2, 3, 5, 7, 11, 15, 22, 30. They grow quite fast.
They do. So what exactly is a partition number, AN?
Well, it's actually quite simple at its core. A partition of a number n is just a way you can write n as a sum of positive integers.
Okay.
And the key thing is the order of the numbers you're adding up doesn't matter. So an just counts how many unique ways there are to do that for n.
Right. Maybe an example would help lock that in, like a 5 is 7 according to the sequence. How does that work?
Good idea. So for n5, we need sums that add up to 5. Let's list them. You've got 11, 1, 1, 1.
Okay, 5, 1.
Then 2, 1, 1, 1.
Okay, using 2s now.
Then 3, 1, 1, and 3, 2.
Getting bigger chunks.
Almost there. 4, 1. And finally, just 5 itself.
Let's see. 1, 2, 3, 4, 5, 6, 7. Got it.
Yeah.
A5 is indeed 7.
Exactly. It seems straightforward, right? But what's really remarkable, and this is the crux of it, is where these numbers appear. They pop up all over mathematics.
Yeah, the sources suggest it's not just combinatorics. It reaches into some pretty abstract areas like group theory.
Precisely. It's not just like combinatorics, there's combinatorics too. But yes, group theory is a big one. AN is actually the number of conjugacy classes in the symmetric group SN.
SN, the group of all permutations of n things.
Correct. And it's also the number of irreducible representations of S. These are like the fundamental building blocks of the group's structure.
So the number of ways to add up to n mirrors the structural complexity of shuffling in items. That's unexpected.
It is. It shows this deep connection between simple addition and, well, much more complex algebraic structures. It's not just a coincidence.
Okay, that's already quite a bridge. But it goes further into algebra too, right? Something about abelian groups.
Indeed it does. Another quite surprising connection, AN, is the number of distinct abelian groups. Those are groups where the order of operation doesn't matter of order p and n.
P to the power of n, where p is a prime.
Any prime p. And the amazing part, the number of groups, AN, is the same regardless of which prime p you choose.
Wow. So the way you partition n dictates the number of these group structures universally for any prime base p.
That's the idea. It's about the structure of n itself combinatorially.
Okay, my mind's slightly blown already. Does it connect to anything maybe more visual? Or maybe things used in other fields like probability?
Funny you should ask. Yes, to both. In graph theory, believe it or not, AN counts the number of rooted trees that have n plus 1 nodes and a height of at most 2.
Rooted trees. Okay, I can picture those.
And more recently, connections have been found to sigma-algebras. AN is the number of non-isomorphic sigma-algebras on a set with n elements.
Sigma-algebras. Those are crucial in probability theory, right? Collections of sets for defining measures.
Exactly. So it touches combinatorics, group theory, algebra, graph theory, and even the foundations of probability. Quite a reach.
It really is. So, how do mathematicians actually study these numbers? With them appearing everywhere, what tools do they use?
A really central tool is the generating function. It's a way to encode the entire infinite sequence into a single expression.
And what does that look like for partition numbers?
It's a beautiful infinite product. The product over all k greater than 0 of 1 divided by 1 minus x to the power of k.
Product KM1, 1xk.
Okay, if you were to expand that product out as a power series in x, the coefficient of xn is precisely an, the nth partition number. It holds all the information.
That's elegant. And I assume some major physicists worked on this. The sources mention Hardy and Ramanujan.
Oh, absolutely giants. Their work was groundbreaking. They developed this incredible asymptotic formula.
Asymptotic means it tells you how an behaves for really large n's.
Exactly. It approximates an as roughly 1 divided by 4 times n times the square root of 3, all multiplied by e raised to the power of pi times the square root of 2n's over 3.
Whoa. Okay, that's specific. But it gives a sense of how incredibly fast an must grow.
It does. Exponentially, related to the square root of n and the exponent. Their work was a triumph of analytic number theory applied to a combinatorial problem.
Are there other neat properties? The sources mention something about log-concavity and even Benford's law.
Yes. Log-concave for n25 means the sequence grows smoothly in a specific mathematical sense. The logarithm of the sequence is concave.
Okay, that feels like it fits with rapid but maybe somehow predictable growth.
Right, but Benford's law, That one's more surprising.
That's a lot about first digits, right? Like in census data or stock prices, more numbers start with 1 than 2, and so on.
That's the one. And yes, the sequence of partition numbers actually follows Benford's law for a sequence rooted purely in number theory to obey this empirical statistical law. Well, that's quite fascinating.
That is wild. So pulling it all together, this one sequence, A000041, it's like a thread running through so many different mathematical tapestries.
That's a great way to put it. Combinatorics, algebra, graph theory, probability. It connects them in unexpected ways. It really highlights the underlying unity of mathematics.
It's a testament to how simple ideas can lead to incredible depth.
Absolutely. And we're still exploring it. Think about the scale A1020 apparently has over 11 billion digits. Just computing these things is a challenge.
Mind-boggling scale.
And there are still open questions, like Ziwei-Sun's conjecture. He proposed that for n greater than 2 and not equal to 6, an is never a perfect power, meaning it's never xbim for integers x and m both greater than 1.
So, like, it's never a square or a cube, etc., apart from those small exceptions.
That's the conjecture. Sounds simple, but proving it seems very difficult. It just shows, even with well-studied sequences like this, there's always more to uncover in the OEIS. What other hidden connections are waiting?
A really fascinating question to leave us with. Exploring the OEIS certainly feels like an endless adventure. That's all the time we have for this deep dive on A000041. Thanks for joining us.
My pleasure.